In this lecture, we will examine the logical areas that a disk or volume is divided into during a high-level format. In previous lectures, we discussed the first step in preparing a disk for use, the low-level formatting used to place tracks and sectors on the disk platters. Partitioning the disk to create logical volumes or disks, and now in this lecture, we will discuss the next step in the process, high-level formatting. The high-level formatting of a disk or partition writes a boot record, file allocation table with a copy of it, and the root directory to the volume. The remaining area on the volume is reserved for data the volume will hold. Let's begin by looking at the boot record. When we discussed partitions, we mentioned that the master boot record, or MBR, had a physical location at cylinder 0, side 0, sector 1. This location is important since the BIOS or firmware will read this sector first to discover information about the disk, as well as whether or not it is a bootable disk, and if so, where the operating system is located on the disk. The master boot record contains various information about the physical geometry of the disk, the partition table, and the location of the boot volume VBR, which is the volume boot record. Each volume or partition on the disk contains its own boot record. If the volume is bootable, the VBR contains location on the volume of the operating system and a small bootstrap program to load it. It also contains descriptive information about the volume, such as the starting and ending logical sectors, the number of sectors in the volume, and the file system used on the volume. The volume boot record is located at sector 0 on the volume or partition. For the first partition, that is usually the physical sector 63 on the disk, though it can vary. Each volume boot record block ends with the 2 signature bytes of 55AA hex to indicate that this is a boot record. An invalid boot record can make a volume unmountable or inaccessible without special utilities. Since a floppy disk only has a single partition, they only have a master boot record and no volume boot record. Just like any partition or volume, a valid master boot record is required to access the floppy disk. Attempting to boot from a bootable diskette with a missing or corrupt master boot record gives a non-boot disk or disk error message. An invalid MBR on a data diskette results in a general failure. Here we see an example of a master boot record from a hard disk. This disk has 512 bytes per sector and 4 sectors per cluster. It has 2 copies of the file allocation table, which we will be discussing shortly. The root directory can hold 512 entries as opposed to a floppy disk that can only hold 224 entries. It has 32 sectors per track and 64 sides. And think of this as the number of heads to read the data. And this information we are viewing here is reported as logical block information, not directly corresponding to the physical structure of the disk. The total number of sectors is 196,576, but there are only 196,573 available to DOS for storing data. And this is because the first couple sectors are going to be used to store information like the master boot record. And lastly, you can see we have a FAT16 file system. Here you can see the specific areas in the logic format of this volume. In sector 0 is the boot record. In sectors 1 to 100 we have the file allocation table. Sectors 201 to 400 have a copy of the file allocation table. The root directory is stored in sectors 401 to 432, and the remaining area of the volume is available for data files. So let's move on and look at the file allocation table, or FAT. The file allocation table is used to maintain the clusters used by every file that the file system manages. Remember, the operating system and file system can only access the disk volumes by clusters, not individual sectors, so our FAT manages the files at the cluster level. Let's look at a system that uses 4K clusters. These clusters are made up of 8 blocks or sectors. The file allocation table will contain an entry for every cluster on the disk. If we have a file that has a size of 14 kilobytes, it'll need a total of 4 clusters or 16 kilobytes of disk space. If a file needs more than one cluster, The FAT creates a chain of references with each cluster entry pointing to the next cluster in the chain. Here you see the second column of the file allocation table that contains that information. In the system file directory, the entry for our document will have the location of the first cluster in the chain. In our example, that's cluster 45. We use that as an index into the FAT. To look at the second cluster in the chain, we look into the second column, and we see that it is cluster 46. The next cluster is cluster 49, and notice that this is acceptable to jump around in the table. This is necessary because as files are read, created, modified, and deleted, areas available on the disk for files may not be in consecutive clusters. The next cluster is cluster 50, and this cluster has an end of file entry, so this is the last cluster in our file. Notice here we have a small two-cluster file that is stored in between portions of the larger file. This is perfectly acceptable and actually quite common. Clusters that are free and available to be allocated for new files are marked with 0 hex. Clusters that have bad sectors and cannot be used are marked bad with the hex code FF7. It is actually possible to hide evidence by using a disk editor to mark sectors as bad even though they contain valid data. The use of normal applications will not overwrite that data, and it will not show up in user file management tools. Lastly, our file only needed 14 kilobytes, but we had to allocate 16 kilobytes since that was the closest multiple of our cluster size. The extra 2 kilobytes of unused space is called file slack or disk slack. We will be coming back to that and discussing it more later since it is an important concept in forensic analysis. Here we see a file allocation table in a disk editor. The cluster highlighted is the first cluster available for data after the logical volume structures, the boot record, FAT, and FAT copy, and root directory. It'll normally be at cluster 2. The file we're examining is c/io.sys, and you can see that in the lower left-hand corner. It begins at cluster 2, continues to 3, 4, 5, 6, and at 6 we reach the end of file. If you look through the cluster numbers here, you can follow other files through their cluster chains also. The size of a disk or volume is limited and is based on the number of bits that are used to represent the cluster number in the file allocation table and the number of sectors in a cluster. For example, FAT16 uses 16 bits to represent a cluster number, so it can manage just over 65,000 clusters. The largest cluster size allowed in FAT16 is 64 sectors, or 32 kilobytes. If we multiply the maximum cluster size of 32 kilobytes times the maximum number of clusters, we see that the largest accessible data area on a FAT16 volume is about 2 gigabytes. That is why many disks, volumes, and memory cards were restricted to a 2 gigabyte size until the last few years. The operating systems and drivers relied on FAT16 and so were unable to access data on a larger volume. The actual cluster size on a volume is determined by the operating system and file system, so as to balance out the amount of disk slack that may occur with the need not to have too many clusters in a chain for larger files. Some disk utilities will permit you to change the number of blocks in a sector when performing a high-level volume format. The next logical area for us to examine is the root directory. Each volume or partition must have a root directory. The root directory contains an entry for each file or subdirectory at the root level in the file system. The root directory itself is just a file with information on other files and directories. Similarly, each subdirectory is a file that contains information about the files and other subdirectories in that subdirectory. And with this information, we can build a tree that represents the file system on the volume. The total size of the root directory is fixed. On a floppy disk, the root directory can hold only 224 entries. On most hard disks, the root directory can have up to 512 entries. That means we can only have 512 entries, files, and subdirectories at this level. Each subdirectory is actually a file located somewhere in the data section of the disk, And so the count of entries in the root directory does not need to count the files and subdirectories inside each of those top-level subdirectories. Directory entries are normally 32 bytes and can contain references to the file or subdirectory name or ID. We cannot store the entire human-readable file name along with other file information in just 32 bytes, so often it may be just the older DOS 8+3 format, which is an 8-character name and a 3-character extension that's used. Subdirectories are treated similar to files, except that they will always fill an entire cluster, so there will be no slack in clusters with subdirectories. As mentioned earlier, the root directory has the starting cluster number of the file or subdirectory, and it has the size of the file in bytes. Important date-time groups for the file, such as creation time, modification time, and last access time, are stored in the root directory, along with important attributes such as: is the file read-only? Is it hidden or invisible? Is it a system file? Is it an executable file or a program? Is this entry a subdirectory? Finally, we have the data area of the volume. This is where all the digital data is stored. This area can also contain erased or hidden data. The clusters of the data area are numbered sequentially, usually beginning with 2. Since the cluster numbers are a logical reference, they do not necessarily have a direct correspondence with a specific platter, head, or side. An important forensic concept we mentioned earlier is that of slack, unused space at the end of a sector or cluster. In our example, we had disk or file slack of 2 kilobytes since the operating system had to allocate 16 kilobytes for our 14K file. File slack is the data that's found in the unused blocks of a cluster in a situation such as this. Here we have our 14K file, and here are the 4 clusters that we use to store our file. When our file is saved to disk in those 4 clusters, we end up with file slack in the last half of the last cluster. This area that is not used by our file will contain data remnants of whatever was stored there previously, files, directories, or whatever. RAM slack is the data found at the end of an unused block or sector. Originally, if a file did not exactly fit a 512-byte multiple for its size, the operating system filled in the remaining bytes with whatever was in RAM following the file. This had the potential to contain useful information to the forensic investigator. Now, operating systems ensure that RAM slack is filled with zeros as a security measure. So, if here we have the sectors that make up the clusters in our file, this area here would be the RAM slack that resulted from our file not being an exact multiple of 512 bytes in size. And those are the logical areas of a disk volume created by a high-level format.